So in our last video we looked at the exponential growth of the coronavirus, and we particularly looked at this chart looking at the doubling rate every 3 days. Okay, so you can see how it multiplies by 2 every 3 days. We started with 50 people. That was the 5 known cases on Saturday afternoon, multiplied by 10 to give us the actual number of cases. At least that was the estimate we used, although I think it's probably larger than that. And then from that initial 50 people, then it doubles from there. And so we were able to construct this model. And now what I want to do is look at it, relate it back to the equation of an exponential function that we saw a couple videos ago, where y equals c times a to the x. A to the x is your exponential part. And what makes exponential functions unique is the fact that the exponent contains the variable. With all of our polynomials and rational functions and other things we've seen, quadratics and linear functions, the variable is always in the base. It's like x to a power, x to the second, or something like that. But here we have the x up in the exponent now, and the base is constant, so it just kind of flips the roles there. And so in the example of the coronavirus, the y-intercept, which is our initial value here, was 50, right? That's where the x value, or the days, are 0. And then the growth rate is this doubling, so it's a 2. So the formula then that would represent this exponential growth would be 50 times 2 to a power. Now we were using x to be the number of days. In this representation here, x would be the number of doubling times, which are 3-day periods. So if I want to stick with x being the number of days, I actually have to think about this in terms of the powers of 2, the number of factors of 2. Every time you double, you want to go 3 days. So 1 factor of 2 should be 3 days. 2 factors of 2 should be 6 days. So if I want to insert a 6, I only want 2 of these 2's. So I want the power to be 2. If I insert a 12, for instance, I actually only want 4 2's. So I want this to be a 4 up here. So in order to get a 12 down to a 4, I need to divide by 3. And so I take the number of days, divide it by 3, and that will give me an exponent, in this case for the doubling time being every 3 days. And if you think about that, it kind of makes sense. If I throw a 15 in for x, divided by 3, I get 5. 2 to the 5th power, 1, 2, 3, 4, 5 2's. Okay, so I should get, the exponent should match up to the number of 2's that lead up to that number. Okay, so this is a good model. Sometimes we have to do a little bit of trickery with the exponent, but generally speaking, the problems you guys are going to see in this section, you're not going to see that. You're generally just going to have an x up there. Okay, unless we're doing like a transformation, like a horizontal shift, you might see something different. We looked at horizontal shifts, I don't know, back in like chapter 3 or something, and so those shouldn't be new to you. Alright, so at this point I'm going to just define the variables. X is the number of days, and y is the number of cases, okay, of the coronavirus. Okay, so a couple things I want to point out. With this growth, if you were to chart these numbers here, or graph them out, it's going to look a little bit strange. Hard to draw, I should say. Maybe not strange, but hard to draw. And the reason it's hard to draw is because of how quickly it grows. In fact, I probably won't even be able to fit all of the data on this chart unless I'm really careful. In fact, let's just do this. Because the highest value on my table is 1600, and that occurs 15 days out, I'm going to start there and kind of work my way backward. Okay, so let's say we had 1600 here, and that's at 15 days out. So I should have 0, 3, 6, 9, 12. There's 15 right there. Okay, so 15, we go up, place our point. That's about 1600 cases. Now at 12 days you have half of that, which was 800. And then at 9 days you have half of that, which was 400. This might start to look a little familiar if you've been following my videos. 6 would be at 200, that's half the height again. So right about there. 3 would be 100. And 0 would be 50. So that's right above the x-axis. Okay. And so the growth is starting out kind of slow, but then it turns and starts to increase super rapidly. In fact, by the time we get out to 30 days, this thing is going so fast, you know, it's almost looking vertical. It's going so fast. It's not vertical, but it's flying. Okay. This type of curve that's shooting up like this, called an exponential growth, okay, because it is always increasing. And some interesting features of this graph. First of all, we know the y-intercept is at 50, right? So the y-intercept is at 0, 50, or generally speaking 0, c. Okay, the x-intercept. Well, we talked about this a couple videos ago, the fact that this thing gets close to the x-axis but never actually hits it. It's what we call a horizontal asymptote, so there is no actual x-intercept because it never gets down that far. But we do have a horizontal asymptote. And that is on the x-axis. Okay. Generally speaking, these exponential graphs will have horizontal asymptotes on the x-axis, unless there's a vertical shift, which we've seen, you know, when we did our transformations. There's also a domain and a range, and I want to talk about those for a second. I think those are fairly important. In any exponential function, you can plug in any value you want. So in this x value, I can plug in positive numbers. I could even plug in negative numbers. I could look at how many cases of coronavirus happened last week. Those would be like the negative, the days in the past. Okay? And so you can still look at those things and project them out, positive and negative, and 0. Decimals, fractions, anything goes. When you plug into an exponent, exponents can be anything. And so the domain on this is going to be all real numbers from negative infinity to infinity. Okay. The range, however, is a little bit different. You'll notice all the positive values are hit, right? This graph is going up indefinitely toward infinity. But when it comes down on the left here, it gets smaller but never hits the x-axis itself. It never drops below the x-axis. And so negative numbers and 0 are not in the range, but positive numbers are. So the positive numbers are all numbers from 0 to infinity, not including the 0. And that would be the range. Okay. Now, in the first video for this section, we looked at exponential decay from the March Madness example. And we said that the a value is what controlled the difference between the decay and the growth. In that example, the a value, the March Madness example, the a value was less than 1, and that created a decay. And that's basically because the rate of change, every time you go from one value to the next, it's being cut down. Okay, if this multiplier is less than 1, it's like a half, you're cutting it in half every time, so you're going to be decreasing. Okay, and of course the a value has to be positive, so I'm going to go ahead and put another side to this inequality. It can't be 0 or less, otherwise negatives don't really work for bases. There's some reasons because of roots and square roots and things like that we can't put negatives in the base. Alright, and now the other thing, this example has a base that is greater than 1. And it's the greater than 1 bases that create the growth. Okay, that's like the doubling. So instead of cutting it down, you're building it up and growing it. Okay, so that's when your a value is greater than 1. That would give you exponential growth. Okay, so you've got your decay and you've got your growth. Now, some very common applications of exponential growth. Obviously, we've seen the doubling time for a virus. Really, any population has this sort of growth to it. And financial interest values have a exponential growth to them. Lots of different natural phenomenon and things in economics that have this sort of growth or decay associated with it. Alright, in the next video I'm going to talk about a very special number that goes along with this topic. It's the number e. So check out my next video and don't forget to like and subscribe.